So I was told that maybe people didn't all know what Boolean circuits are, so I'll tell you what they are just in case. So a Boolean circuit, give you an example. So here would be an example of a Boolean circuit over 3 Boolean input variables. And the intermediate gates of the circuit, it's a directed acyclic graph. Every gate, every node of the graph has fan-in 2, and it computes the Boolean function. So this is just the logical AND of x2 negated. This means negated. So this is the logical AND of x2 negated and x3. This is the logical OR. So for example, if the values were 1, 1, 0, 0, then this computes a function in the obvious way. The OR of these two values is 1. Pardon me?
The 0, 0 doesn't.
Oh, sorry. Sorry. Thank you. Good. Did I make any other mistakes? So compute the intermediate, so that you compute the intermediate circuits in a bottom-up way. So the AND of these two, 0, the OR of these two values of 1, and now we have 1 and 0, the OR of that is 1, and if I did it right, then that's the value output, okay? And what I'm interested in, central object of study, is to try to understand the minimal size of a circuit that computes a given Boolean function. And we'll focus mostly on these two examples. The clique function, where the graph is actually, the input is actually a graph on n vertices, so it can be described, say, by an n by n matrix of Boolean variables, where the ijth entry tells you whether or not the ijth edge is in the graph. And you want to accept the graph if and only if it contains a clique of size, say, at most c. Okay, and you should think of c as being big, like something that's maybe square root of n or linear in n. Okay, so the obvious algorithm for solving that would be to just run over all subsets of size c and see if it contains a clique. And that's not a good algorithm. It runs in time roughly n to the c, which for c large would be exponential in the input length. And the reason we care about the circuit complexity is that if you have a polynomial size circuit for a Boolean function for every input length, so for every input length you have a circuit that solves the problem on that input length. If you have such a family of circuits of polynomial size for every n, then that implies the non-uniform version of that the function is in P. So said the other way around, if you can solve a problem in polynomial time, you can extract from the algorithm these family of small circuits. Okay, does that make sense? So showing that some explicit function in NP doesn't have polynomial size circuits proves that P doesn't equal NP. And that's why we care about it. It's a stronger version because it proves this non-uniform, proves it in this non-uniform model where we're allowed to totally change the circuit for every input length. Okay? Just say a couple of other basic things. One thing to notice is that if you didn't care if the function was in NP, which is non-deterministic polar time, if you just wanted to show that some function required large circuits, then you can just use a counting argument. So size, if you can count any size S Boolean circuit. By size S, I mean the number of gates in the circuit. So any size S Boolean circuit can be described using about order S log S bits. So I can just specify for every gate whether it's an AND or an OR gate, and then I can specify what the input gates are to that circuit. And so if S is, as long as S is bigger than n, this is going to take roughly order S log S bits. And so then the number of Boolean functions computed by size S circuits is exponential in S log S, but the total number of Boolean functions on n bits is exponential in 2 to the n. So if S is polynomial, it's very rare to be a function that's computed by a small polynomial size circuit, because there's just so many more functions than there are polynomial size circuits. So the reason the problem's hard is we want to come up with a function in NP, such as one of these two functions. Okay? And this was the other classic example that we'll use, the three-set problem. Basically you're given a bunch of clauses, which are disjunctions of literals over n variables, and each clause has size 3. And you want to know if it's satisfiable. And we'll encode this as a vector of length. Basically, we'll have one bit for every possible clause of size 3 over the n variables. And so this vector will represent a particular set of clauses, and we want to accept if the corresponding CNF is satisfiable. Okay? So they're both monotone functions in NP, so we'd love to prove, as strong as lower bounds as we can on them. So let me just say one other restricted problem that we care a whole lot about that's still wide open is if we we can restrict attention to Boolean formulas instead of Boolean circuits. So a formula is like a circuit, except that every gate has fan out 1. So in other words, you can't reuse a computation. So if I wanted to compute this function with a formula, I'd have to replace this subcircuit twice and use it once to feed into here and once to feed into here. So it should be easier to prove monotone, or it should be easier to prove formula size lower bounds. But we don't know how to do that either. Okay. So I'm not sure if I'm going too fast or too slow, so if you can, if you have questions or if you want me to speed up, just let me know. Okay, so the milestones so far that were two big milestones from the 80s is a result by first Xipser, then Yao, then Hofstede, that proves exponential lower bounds on the size of circuits, but with a restriction that the depth has to be constant. In fact, the depth could actually go up to log n. And that was a big breakthrough result from the 80s. And the other beautiful result from around the same time period is a result by Razborov showing that if you restrict to a monotone function, such as the clique function, and then you look at monotone circuits that compute the monotone function, so you're not allowed any negations, then he proved that clique can't be solved with even sub-exponential sized monotone circuits. Okay? And these proofs really they crucially use this structure versus pseudo-random versus structure decomposition sort of paradigm that's come up a lot in many different areas in extremal combinatorics and additive combinatorics, in pseudo-randomness in computer science and lower bounds. So what I want to do is first describe to you, remind you or tell you about the sunflower lemma and show how show how Razborov used it to prove the monotone circuit bounds, and then show a new proof of the circuit lower bounds using this paradigm of converting the problem to a communication problem, and then prove what we call lifting theorem that allows you to kind of take a simple type of a lower bound and kind of automatically convert it to a lower bound in a more complex model. And using the lifting theorem, we'll show how to reprove Sasha Razborov's result as well as many other results. Okay, we'll see how far we get. Okay, so the sunflower lemma, you have a k-uniform set system, so that means all the sets in capital S have size k. And the lemma states R is a parameter that depends on P and K, and you want R to be as small as possible. And the lemma states that as long as the set system is large enough, at least as big as R to the K, then it must contain a sunflower with P petals. And a sunflower looks like this. It's a subset of the sets in the set system where they have a common intersection, which is the core, and then the other parts are all mutually disjoint.
Sorry, to understand what k-uniform set system?
Yeah, so all of the sets in capital S have k elements in them.
Oh.
So there's some universe, say U of size n, that doesn't enter the parameters here. And each of these sets is a subset of size k of the universe. And you say that the set system has a sunflower with p petals if there's p sets, like this is p equals 7, where they have a common intersection, which is the core, and the rest of them are disjoint. Okay?
And is P related to R?
Yeah, so I'll show you that now. Yeah. So it's been known to be true for a while when R is k times p roughly. It's a little bit better than that, and it's conjectured to hold for R that's O of p, but we don't know how to prove that yet, or even if it's true. And a very quite new result by one person in the audience, always love it, Wu and Zhang, made major progress on this and got it really quite closer to p. They show that it's true for R equals p log pk. We have another expert in the audience because Noga also was one of the people that improved Sasha's proof of the sunflower, improved his proof of the monotone circuit bound using the sunflower lemma. So I know less about this than some of these people, but nonetheless, that's how it goes. Okay, so the proofs all use this. Well, I don't know if they did when they were first, the first proof of it. The proofs go by induction, but the basic concept is this idea of spreadness or being not dense. So a spread is a word that I guess Talleyrand was a notion that he defined. Correct me if I'm wrong, I'm pretty sure. Anyways.
You didn't call it spreadness.
Okay. I was trying to track down the, okay, anyways. Somebody, it's been defined in many communities. I know he's one of the people that was one of the original people that defined it. But anyways, you can call a set system R spread if for any subset Z of the universe, there's at most R to the k minus size of Z sets that contain Z. So intuitively,
what is the impact of this on the sparrow? Better exponential outbound?
You mean these parameters? Right.
Or will you get to that?
So I think that I think that if, so I'm not 100%.
It's minor.
Well, no, but if you can prove the conjecture, I think if you can prove the conjecture for P, you might get linear, you might get truly exponential bounds. Oh, sorry. Yes, in the big scheme of things, it's minor. It's like right now the best is 2 to the square root of n, which was obtained by your results, by Ben Rossman and some other people. And anyways.
Even I think the lemma of first world is not exactly sunflower.
Right.
Because for that the bound that exists is exactly tight.
Right.
So it is not, but yeah. But anyway.
Yeah. So they're all of the form true to the n to the epsilon, even with the basic one. Yeah. So here's the basic one. We're going to show that, well, first of all, assume the lemma says that if the set system's big enough and it's spread, then it contains p disjoint sets. Okay? And the proof, assuming the lemma, is very easy. It's a decomposition result. It's by induction, but k equals 1 is obvious. And for k bigger than equal to 2, you look at the set system S. The sets all have size, k. And either it's spread or if it's not. If it is spread, then by this lemma, you're done, because p disjoint sets is a sunflower where the core is empty. And otherwise, there's some Z, some subset, where there's a lot of sets that contain Z. Okay, so it's like dense in Z. And in that case, you're just going to recurse on S prime, which is all the sets in S. I think people call it the link, but all the sets in S that contain Z. Okay, and sort of by definition, that's big enough that you can recurse. Okay? So really, the whole point is to prove the lemma for as small a value of R as you can. So the simple one is really easy. So if B is your, let's assume B is your, so now I want to prove this lemma, just the simplest argument that proves the lemma for R equals P times K. So let B be a maximal collection of disjoint sets that are contained in S. So just keep adding sets to B that are from S as long as they're disjoint until you can't do that anymore. And assume that T is less than P. So the number of sets that are disjoint, pairwise disjoint, is less than P. Then by averaging, some element in the union of these sets is contained in the size of S divided by the size of P times K sets. Because every set in S intersects this family, and there's at most T times K elements here. Okay. So some elements contained in that many sets, and for this choice of parameters, this is going to be at least pk to the k minus 1, so that contradicts the fact that it was spread. Okay. Any sense? So it's just like a density argument. So in the more complicated one, which I'm not going to describe, it's a more fancy proof of this lemma that uses like coding arguments similar to similar to Hofstede's proof, or Rasbroff's proof of Hofstede's switching lemma, which was used to prove the bounded depth lower bounds that I also mentioned. So, but anyways. Okay, so now I want to try to explain how the sunflower lemma is used to prove Rasbroff's theorem. Okay. Oh, I want to mention one other thing, which is going to come up when I talk about lifting later. So there's various ways that you can modify the sunflower. It's fairly robust to changes, reasonable changes. So one reasonable change is block respecting sets. So if you have a universe U, now instead of just the sets being arbitrary sets, we're going to force them to be sets where you divide up the universe into k pieces, and you pick one element from the first piece, one element from the second block, and so on. Okay, so a set system is block respecting if what I said holds. For every set in the set system, you have exactly one element from each block. Okay, and same sunflower lemma for a block respecting set system. As long as it's big enough, you want to say it contains a sunflower with p petals. And it turns out that this version is roughly equivalent to the other version. So in the sense that even if I can prove the strongest version of it, where r is p, I can prove this version with that strong parameter if and only if I can prove the other version, okay? Where r is order p. So I'm going to use this version because it comes up later and I somehow like it better. Okay. Okay, so we want to show that, so again, we have a monotone circuit, so it looks like this, but it doesn't have any negations, so these have different values. And we want to show that any monotone circuit that's too small, x of size less than 2 to the n to the epsilon, for some epsilon, can't accept. We're actually going to prove it can't compute clique by coming up with a set of 1 instances, which are graphs that have cliques of size c plus 1 in them. In fact, that's all they'll be. They'll be graphs just consisting of a clique of size c plus 1. And the no instances will be graphs that are called C co-cliques. So that means they'll look like this. So a C co-clique is a partition of the universe into C pieces. So here C is 5. And then you have all the edges. So you can think of it as a coloring. So you have all the edges between any two pieces. And within a color class, there's no edges. Okay? So it's pretty clear that this does not have a C plus 1 clique. Okay? So these are going to be the 0 instances. And then the 1 instances, they'll just look like, you'll pick 5 elements. 6, thank you. You'll pick 6 elements from the universe. It's the same universe, so there's n vertices in both cases. So the S instances will have 6 special vertices with all the edges between them and no other edges. Okay? So even separating these two classes of graphs, it's kind of trivial if we have negations. I hate to point that out, but it's actually pretty trivial to separate these two things if you don't have negations. You just have to count the number of edges, for example. This is hard for monotone circuits. Okay. So that's what we want to show, that any monotone circuit can't say 1 on all of these and 0 on all of these. Okay? Okay. And the basic idea behind the proof is to show that as long as we're going to look at every sub-circuit of the circuit, and we're going to show that as long as we're going to basically approximate each sub-circuit by a very simple object that's going to be, well, here it is up here. So we're going to bottom-up approximate every sub-circuit C in this. So we assume for sake of contradiction we have a small circuit. So we're going to bottom-up approximate all the sub-circuits, each of them by a different k-uniform and block respect. Doesn't have to be block respecting, but that's how I like to do it. K-uniform block respecting set system. Okay, and the way you should think of a set system corresponding to a gate or to a subcircuit is so it's a set system over the universe n, and the sets are going to have some size k. Okay, and k is going to be smaller than c. C is the clique size. So think of c as being whatever c is. K is going to be about square root of c. Okay, and you can think of c as being square root of n if you want, or even n over 10, and k is going to be square root of that. Okay. So what we're going to do is approximate each subcircuit by one of these k uniform set systems, and you should think of each set in the set system as naming k vertices, and that set is going to correspond to the clique on those k vertices. Okay, so the circuit that's going to correspond to this k uniform set system is going to accept a graph if and only if it contains a clique on one of those subsets of vertices specified by the set system. Does that make sense? Okay, so we want to show that for every gate, the fraction of new errors that gate introduces is small. So, and then secondly, and then by just adding up all the errors, if the circuit's small, that will imply that there's a simple approximator, namely an OR of square root of c sized cliques that's going to approximate the whole thing, and it's quite easy to show that that's a very bad approximator for separating these from these. Okay.
Define error.
So I will in a minute, yeah. So error is basically going to be the number of graphs of one of these two types that the circuit got right before, that the two subcircuits below it got correct, but a new error was introduced at this gate. Okay. So I'll show you. We'll do that in the next slide. Is the high level clear? Yeah? Okay, so here's how we'll approximate. So here's a circuit, and let's say we've already approximated this subcircuit C and this one D. Okay, so we have a set S sub C corresponding to this circuit. It's a set system Q1 through Qm. So in other words, the approximator for this circuit accepts exactly when the graph contains a clique on one of those sets Qi. And likewise, we have the set system for this one, and now we're taking the OR of these two things. Okay, so when we take the OR, what we'll do is we'll just take the union of all of those sets, the Q's and the R's, put them all together. But we want to maintain that, I forgot to stress this on the previous slide, we want to maintain that the number of these sets in the set system is at most m, and m is the same parameter that we were using in the sunflower lemma. So m is like r to the k, or pk to the k. Okay, so every subcircuit should be approximated by a k uniform set system where the number of sets is little m. Okay, so what happens now is if you take the union of these, you might end up with 2m sets instead of m sets. So now we have to get rid of some of those sets to get back down, to prune them somehow to get back down to m. And the way we'll do that is using the sunflower lemma to basically repeatedly, I'm going to describe it in two ways. So one way is we'll just repeatedly, if the set system's too big, then we know by the sunflower lemma that there's a sunflower, so we'll replace the sunflower by its core, okay, and then we'll continue. Okay, and we'll keep doing this until finally we have no more sunflowers, and then at that point we'll know for sure that the set system has size at most m.
I'm probably not your intended audience, but
No, yeah.
It's not clear to me how one represents a computation of a subcircuit to a collection of subsets. Is that obvious?
So maybe it'll help you to say, so you start at the bottom, and this is going to correspond to all graphs that, so the input to the circuit are edges of the graph. So it'll correspond to cliques of size 2. So you'll accept exactly if that edge is in the graph, which is like a clique on those two things. Okay, and then we're going to recursively define the set systems going up in the way that I'm describing.
Another way to say it is that if you have a set system, you think of the Boolean function, which is the O over all the sets of vertices, and the and over all the edges they span. And the and over all the edges span in a set of vertices of size whatever c is a clique on this. So it's an O of cliques. So every approximator is just an O of m across m cliques.
So let me just say something that's maybe now is the time to say. It's not at all obvious a priori how to do this, because the circuits can be super complicated, and they might involve all sorts of complicated information about the graphs, not just is there a clique slapped on this? You know, this is a super simple way of you know, describing this circuit. You know, I'm just going to try to describe it by the dumbest possible thing, which is the cliques that it can sort of recognize. Whereas in reality, it could be who knows what kind of fancy computations it can be doing in P.
I see.
So I'm not sure if that helps.
I missed this. This is like this approximation is specialized to the problem of taking cliques.
Correct. Yeah, and we'll see when we get to the more general thing. We'll see how to do this in general. But yeah, I'm just doing it now for. Yeah.
But the fact that this approximation works to prove a law shows that monotone circuits are extremely weak. That's the only thing they can do. Really, the consequence of the proof.
Well, that's a glass half empty point of view, but yeah. Okay. So anyways, the other way I want to describe this is as a decomposition process. So you start with your set S, okay? And remember that I'm thinking of it as a blockwise. So each of these QIs, you partitioned a priori, you partitioned your whole universe N into K blocks once and for all. And then each of these sets is a set where you picked one purple guy from each block. So each QI is a set of size K chosen by picking one element from each block. So that's a picture up there of one particular set. Okay, K is like 1, 2, 3, 4, 5, 6, 7, 8, whatever, 9. Okay. And then what we're going to do here is we're going to view, I like to think of S now is like a distribution over, so you have K blocks, and within each block, so I'm thinking of like, for a given block, you can look at the projection of the set system on that block. So for example, how many times do the sets pick the first element of the block? How many times do they pick the second element? So you can look at like the probability for a given block that, you know, that a particular guy was chosen. Okay. Likewise, for a pair of blocks or for any subset of blocks, you can look at the density or sort of how likely it is that a particular value was chosen, as opposed to them all being uniform. Okay. And what's happening so you start with S, and you can view it as either being spread or not spread. Spread sort of means that everything's uniform. You don't really have much information about any of the blocks. Okay. And if you're not spread, then that means that there's some, remember there was some Z value. So there's some, in this case, there's some set of blocks. So I1 is, you know, a particular subset of the K blocks, maybe the first two. So there's some subset of the blocks and a value for those blocks. So maybe the first block you pick the second one, and the second block you pick the first one, where that's too likely. So it occurs in too many sets. Okay, so that's what it means to not be spread. And in that case, what we're going to do is, you know, we're going to decompose S into those sets that contain this value, this too likely value alpha. Okay, and if we assume that alpha is like, that I1 is a maximal subset of blocks with this property, and that alpha is a value for those blocks that are achieving this too high density condition, then when we restrict to this set S prime, where those blocks are fixed to that value, this will now become spread again. Okay, and then we take the rest of the sets that weren't in this collection here, and we continue to decompose the same way. Okay, so that's a little fancier of a way to describe what's happening. That'll be helpful later on.
So one thing, how does K relate to C?
Yeah, so K, yeah, I will. So K everywhere is the K from the sunflower lemma, and K is always going to be like square root of C, and you'll see why in the next slide. Yeah. Or something less than square root of C.
So previously, didn't you say that S1, I mean, once you find the sunflower, you replace those
Right. So then, correct. So then what I'm going to do, since this is spread, I'm going to basically replace it by the core, which is alpha 1. And likewise, this by alpha 2. And finally, when I get to something that's spread, it's just spread, then I replace it by 0. So I'll end up with the approximator for the OR will be just just the sets that are the cores. So these will be sets that have size still at most K. And by the fact that, by the sunflower lemma, we know that the number of them is going to be certainly less than M.
So whenever you Boolean circuit output one, set should be a set in the family kind of corresponding to this assignment, but not the way out.
Right. So on a yeah, exactly. So on one of these graphs, this thing is not going to it's not going to make any mistakes. It's just going to accept more things. So if the bottom two did the right thing on a clique, an OR approximator, when you're approximating the OR of the two subcircuits, won't make any mistakes. So this will only make mistakes on the AND on these graphs. So now we're going to analyze the errors on these graphs. Okay, so now I want to say, so let's take a, when do we make an error? When is this process where we're doing the OR of the two circuits, when does it make an error on a graph like this? Okay, and so what happens when you make a mistake? Well, when you make a mistake, it has to be that, so let's look at, it was alpha 1, alpha 2, alpha 3, so on. So look at one pluck. So one pluck is where we replaced a sunflower that was in the union by the core, okay? And when you made a mistake was when the subcircuits below you did the right thing. So in other words, the co-clique on each of these sets has the value 0, but the co-clique on the inside, on the core part, has the value 1, right? Okay, so how can that happen? Well, it has to be the case that each of these petal parts, the co-clique has to have the property that each of these petal parts has to have at least 2 guys in it that are coming from the same color class. Okay, because when that happens, that's the only way that all of these petals can be 0. Okay, and when you take them out, that it could possibly be 1. Makes sense? And that's now the birthday paradox. So that's why we picked k to be square root of c. So like you have c different possible colors, and you have k different people, and so the chances of having 2 people with the same color, when k is like square root of c, is roughly some constant. Okay, so that's why you're getting some constant less than 1, like a half, to the p, because p is the number of petals. Okay, and again, this is a less than or equal because the core also has to give the value 1, but we're just ignoring that because the core could be empty, so we can't really say anything about it.
You see in the pictures that you don't care the core will be a core. It's just important that the intersection of every pair is equal.
Correct. Yeah, the core is really inconsequential in this calculation. Yeah. Does that make sense? So that's the errors per pluck. The number of plucks is certainly less than 2m. This is an overestimate. And then for this choice of numbers, you end up with that the fraction of errors is exponential in k, and k is some n to the epsilon. So that means, the fraction of new errors introduced at each gate is this amount. So as long as there's not too many gates, the top the top approximator will not have too much error, which will contradict some base case where you just argue that such a simple approximator is going to err on, say, half of the graphs. Okay. So I just did the OR case. The AND case is just a little tiny bit harder. It's really almost the same, so I'm going to not do it. But that really is the whole idea. Okay. Questions? Okay, so just to say, obvious question. So you might be really discouraged by this because these are really super stupid examples of graphs in the sense that it's very easy to separate these with a really small non-monotone circuit. But I just want to say that I'm not so pessimistic because so if you could prove a monotone.
Optimism and pessimism around this, I mean, whether this might lead to something which is not for handicapped.
Exactly. Yeah, so the question is, can monotone circuit lower bound arguments ever lead to proving P not equal NP? And granted, we're far from this, but I just want to point out.
All these results which give non-trivial exponential lower bounds, are they all basically counting that you just don't have enough of circuits, basically?
Yeah, basically, they're all.
No, it's not counting that you don't have enough.
Oh, no, it's not counting you don't have enough.
In a sense, yeah.
You have to come up with some property.
With
So.
this property. No, it's not counting the argument at all. It's a structural argument. But
Yeah.
it's still down to a structural, if I understood correctly, a structural limitation of the number of.
Maybe I'll keep going and we can do it again at the end.
No,
But it's a good
not
question.
counting elements.
Yeah, I think he knows that.
These are
I think he.
small,
Yeah, it's not simple counting. It's much more complex. But maybe we'll. Okay, so I just want to point out something quickly. I don't want to spend too much time on this, which is that if you could get this argument to work for a different family of yes and no instances that had exactly the same number of edges. So if they were say random graphs drawn from G and P, or drawn where you have exactly half the number of ones and half the number of zeros, a monotone circuit lower bound would prove P not equal NP. So this is so-called. Yeah, if you could prove do I have it on here? No, I don't know. So if you could prove a monotone lower bound, but for two different groups of instances, one instance is zero instances, where all of the instances are in some slice of the cube, they all have the same number of ones, then you would prove P not equal NP. So non-monotone and monotone circuit complexity is the same for these slice functions. And it's just because if it's a slice function, then you can replace a negated variable by the sum. So if you know that the number of ones is W, that's the slice, then you can just replace a negated variable by the sum of all the other variables has to be at most W. And that's easy to compute. Yes, very small linear sized monotone circuit.
Is this also approximately, like these two families that are on?
Yeah, that's a good question. So far it seems brittle, but that's the hope for sure. Yeah, it seems like there's a lot we could do, but yeah, I'm still hopeful. But especially for formula size bounds, I'm still hopeful. Okay, so I want to just say a little bit of how to recast this lower bound in this more general context of communication complexity, and then a more general sort of theorem called lifting theorem that allows us to prove Rasbroff's lower bound and many more. It proves other things besides circuit bounds too, but it's what I would call like the meta theorem that's behind his result. And then I could try to explain a little bit how the proof is in some sense very much like a harder version of the sunflower. I mean, it's okay. It's a little. It depends how much you care about parameters, but it is a more complex version of the simple sunflower lemma. The statement of it is more complicated, and what it's saying is more complicated. But the decomposition, the whole idea behind it, is really, very, very much the same. Okay, so circuit. How many? Let me go over it really quick. This is going to look like change of subject, but maybe you all know this because this was obvious result from a long time ago. But communication model is a model of information. It's not really it is a computational model, but you measure information flow. So you have two players, Alice and Bob, and they each hold an n-bit string, and they're trying to compute some joint function of their input. And they have a protocol that they've agreed on in advance. So maybe they alternate. Alice always goes first, sends a 0 or 1. Bob goes next, sends a 0 or 1, and so on. And at the end of the conversation, they should both know the value of the function. Okay? And the communication complexity of the function is the minimum cost over all inputs of length n, so that they can compute the function f on their 2n inputs. Okay? So maybe here's a good example, which is the one we'll use. So this is a communication complexity of a total search problem. So here's a really good total search problem. Alice, you're going to have some underlying function f. Okay, it's an ordinary Boolean function on n bits. But now Alice is going to be given a 1 of the function. So in this setting here, she'll be given one of those 1 graphs. Okay, and Bob's going to be given a 0 instance, so one of the 0 graphs. And their job is to output some coordinate I, so some index where their strings differ. Okay, seems simple, right? And the result is that, I'll skip this. So the result is that the circuit depth, the minimal circuit depth, so the depth is, the length of the longest path from the top to the bottom. The minimal, for any f, the minimal circuit depth of f is pretty much exactly equal to the communication complexity of this Karshmer-Wigderson problem. Okay. And the proof is really easy. It's an equivalence, so there's 2 directions. But the interesting direction is to show that if you have a small depth circuit, then you have a small communication protocol, because that means lower bounds for communication give you lower bounds for circuit depth. And by the way, circuit depth is more or less equivalent to the log of the formula size. So if we could prove lower bounds on the communication complexity of this Karshmer-Wigderson game, polylogarithmic lower bounds, that would prove, formula size lower bounds, which would be a major milestone. So the argument is just, so the players, each of them has some Boolean vector input to the circuit, and Alice knows that the output evaluates to 1 on her input, and Bob knows that the output is 0 on his input, and so they just walk down the circuit, in the obvious way. So they maybe, if it's an AND gate, then Bob knows that one of his 2 subcircuits has to evaluate to 0. So then Bob would say yes. Bob would indicate to Alice whether to go left or right, and if they go left, now they know that their inputs restricted to this half have the property that Alice's output's 1 and Bob's output 0, and so on. So they just trace their way down the circuit. At every point in time, they know a subcircuit of heights 1 less than before, or that they know that subcircuit, they differ on the output, and so then eventually they'll get to an input where they differ. Okay, and the number of bits is just the depth. Okay, so I think this is really, I don't know, somehow, even though it's easy proof, to me it's just really, really great. And there's a monotone version of it, kind of sadly, because we're going to exploit this to get all the lower bounds. So the monotone version of it, the function's monotone, like clique, and same thing, Alice gets a 1, Bob gets a 0, but now they have to find a coordinate where Alice's bit is 1 and Bob's bit is 0. Okay, it's not symmetric anymore. They have to get an input where Alice is 1, and somehow this makes it much harder, and therefore much easier to prove lower bounds. And the theorem still holds in the monotone case. So the monotone circuit depth is equivalent to the monotone communication complexity. Okay. And there's a version by Razborough of this theorem that takes you to the DAG-like case. So it translates DAG-like communication protocols to circuit size rather than formula size. Okay. So directed acyclic graph. I'm not going to define it, but you want to know what a DAG-like communication protocol is?
I just want to know what DAGs.
Oh, okay.
Directed acyclic graph.
Yeah. So you always think of a protocol as a tree, where Alice goes this way, and so it's like a tree. But you can define, and it's not. You have to put some effort into doing it right. But you can define a DAG-like protocol where the protocol can come in again, and you have to be careful to define it so it's not trivial to compute any search problem. But if you define it the right way, you end up with this version. So I'm going to skip that part because that'll take a long time. But there is this version of it. So again, you can go from communication lower bounds directly to formula size, monotone formula size, circuit size, monotone circuit size. Okay, so I want to tell you now about this technique for proving communication lower bounds, and then show you, hopefully, if we have time, how to use that to sort of prove a lot of various, mostly monotone circuit bounds. Okay. You can also use it to prove other lower bounds in other areas, but we'll see if we get to that. Okay, so the idea behind this is it's not. It actually is quite similar to what's going on here, but it might not look it. But the idea is that we want to start with a function or a search problem, little f, and we want to study a simple complexity measure on this, which is decision tree complexity or query complexity. And that is, you look at a model. All it's allowed to do. So it has, n Boolean inputs, z1 through zn, and all it's allowed to do is query a bit, say maybe it queries z5, and then goes left if z5 is 0, goes right if z5 is 1, and then it can query another value and so on. Okay, so it looks like the decision tree, would be like, maybe it would query z1, and then it would query z5, z3, something like that. And then at some point, it's allowed to stop and give an answer. Okay. And the complexity, this is a really simple model. It's super easy to prove lower bounds in this model. And typically, we're interested in the minimal height of a decision tree that solves a Boolean function. Okay. And it's related to Fourier degree of solving the function too. Okay. So what we want to do is take a function f and translate its query or decision tree complexity to the communication complexity of f composed with an inner function g. Okay, so g is a new function that's going to turn it into a communication problem. And so g will have, two inputs. Think of these as real small inputs, like hopefully a real small number of bits. And Alice will get the first half, and Bob will get the second part. Okay, and we'll call this a gadget. And then the communication problem will be to solve f on, the composed function. So solve f on x1, y1 applied to g. This will be like z1 fed into f, and so on. Okay. And Alice will be given the x parts, and Bob will be given the y parts. And they're trying to output the value of f. Good? And the intuition should be that, so let me give you an example. So let's say that f is the set disjointness function, which is just the OR function. So f is the OR function, z1 or zn. And let's say g is the AND function, xi, yi is equal to xi and yi. Okay, then f composed with g is what we call the set disjointness function. So this is going to be 1 if and only if there exists an I such that xi equals yi equals 1. So if you view, so here the gadget is just a 2-bit gadget. So this is 1 bit and 1 bit, and this is just the AND of them. And so Alice gets an n-bit vector, Bob gets an n-bit vector, and if you view them as sets, you want to know, do their sets intersect or not? Okay, so f composed with g is 1 if x and y viewed as subsets of n intersect, and it's 0 otherwise. Okay, and the most obvious way to solve something that's composed like this is to follow the decision tree, the optimal decision tree protocol. So you have a decision tree protocol for f, and the obvious thing to do is for them to simulate that protocol. So start at the top. If the 5th bit was queried, then they compute g on x5 and y5, and so on. And so that always works. So you can always show that whatever the decision tree complexity is, that the communication complexity isn't much worse as long as the gadget's small. And what we want to prove is that for sufficient gadgets, that the converse is true. So that for sufficient gadgets that aren't too big, that the only thing that you can do to solve the problem in the communication world is essentially to mimic the simple decision tree algorithm. Okay, and so that's the statement. That's the interesting direction of a lifting theorem, to show that the communication complexity of the composed function is more or less the decision tree complexity of the base one, of the top one. Okay. And the most interesting case, application case so far, is something always along the lines of this, where it's these total search problems it's this type of total search problem. You have an unsatisfiable 3CNF formula, okay, and the top function f is trying to find a violated clause. So given an input to the underlying variables, output some clause that's made false, okay. So that's little f, and then we want to compose that with some little g and be able to argue that the only thing you can do here is follow the decision tree. Does somebody have their hand up? Okay. So we have these for various types of decision trees and the corresponding types of communication protocols. So we have this is the statement of the one for deterministic decision tree, goes to deterministic communication complexity. And I'm just fixing on this one gadget because it's nice. We can do it with other gadgets, but this one's particularly nice. It's like a universal gadget called the index gadget. It's lopsided, but it's not such a big deal. But you think of x as a pointer into a bigger string y, so x has length log m and y has length m, and then the value of the gadget is just the bit pointed to by x in y. Okay. So for that choice of gadget, we have the lifting theorem for the deterministic case, the randomized case, and even for the DAG case. And by we, I mean not just me, this is lots of people's work. So if you think about this applied to applied to the case where F is the search problem associated with unsatisfiable CNF, what you end up with is something really nice, which is saying that it's taking you from a proof measure of proving that this formula is unsatisfiable. Resolution is a very simple proof system, and it's saying that that's equivalent to the proof complexity of the lifted unsatisfiable formula for a much more complex proof system where the lines can be computed by communication, small bit communication protocols. In particular, threshold, like cutting planes or any proof system that's allowed to reason with, linear inequalities is covered by the right-hand side. So it's a way to get lower bounds for like cutting planes types proofs from very simple resolution bounds. Okay? Does that make sense? I don't know if I'm going too fast now or questions? Good?
Maybe you can explain again, or at least the example a little bit more.
Right. Okay. So we said that F was just a search problem associated with the CNF. So given a bunch of clauses, output a violated clause. So what resolution is tree-like resolution is really just all it is it's a decision tree that solves the search problem. And the height of the decision tree, corresponds to the depth, the best depth of a resolution proof. And so that's why that's why you can think of the decision tree height for the search problem is the same as the resolution depth for C. It's almost by definition. And then the right-hand side was we said that the decision tree complexity of the base function, which is finding a violated clause, corresponds to the communication complexity of the search problem for the lifted one. So what is that? Well, that's a search problem for some other CNF. It might not be 3 CNF anymore, it depends on the gadget, but it's some other, CNF formula that's not too big. And so now, since you're allowed communication, instead of just querying, you can sort of replace these things by anything that you can compute with a small communication protocol. For example, a linear threshold function, you can compute with a small protocol. So it's a little bit harder to see why this side corresponds to the height of like a resolution or a cutting planes type proof.
You're transitioning twice from communication complexity to proof complexity.
Yeah, right. So over here, I'm saying that if you look at the decision tree that solves the search problem associated with an unsatisfiable formula, the height of that will be the resolution height. And over there, I'm saying that you can equate the communication complexity of solving the lifted one with the height of a cutting planes or threshold proof.
You need range values for any of these?
Yeah. So because since the threshold lines could have high weight, you need something more than deterministic for that. But you don't need the full power of randomized. You could use, anyways. But yeah, you need something more than deterministic. Okay, so yeah, so then there's the withdrawal. So I just want to say something about so I have two more things to say. I think I'm going to skip this one and just tell you that you can. I'm not going to prove this. I'm just going to state it. So you can apply the lifting theorem verbatim with a small sort of observation to get the same monotone circuit bounds and more. And the way you do that is this is going to look a little weird, but I'm going to start with an unsatisfiable 3 CNF, and I'm going to lift it. So this is what we've been describing so far. And the claim is that the yes and no instances of this lifted search problem, so I have this lifted search problem, Alice is given the x half, Bob's given the y half, together they're trying to find the violated clause. I actually can view the x inputs to Alice as 0 instances of the k-sat problem, and Bob's input is 1 instances of the k-sat problem. And by the Karshmer-Vigdorsen equivalence, that means that the communication complexity of solving this is exactly the same as the monotone circuit depth of this, and likewise for the DAG case. So the lifting theorem takes me from a simple lower bound like a decision tree bound to a communication bound, and that communication bound is separating yes and no instances of the Kirshner-Wigderson game for this monotone NP problem. So that's like a little reduction that I'll skip. So and the nice thing about it is that you get, you don't just get Razvorov's result. You can play around with it to since you have a better kind of crank. So you can, if you want to separate monotone NC1 from depth log n from depth log n squared, or whatever it is that you want to do, you have this equivalence between the decision tree complexity and this more complicated complexity. So you can use the fact that it's an equivalence to get upper and lower bounds and to get separations for other things. And I think that's probably why lifting's has had so many applications to other areas outside of circuit complexity, because you have this equivalence. So you can play around with it in the simple, intuitive model and automatically get the result in the stronger model. So I wanted to get back to sunflower. So let me just try to, so I'm going to just remind you this will just take me 2 minutes. This is really just going to be superficial. But so I want to just say something about how lifting theorem is related to the proof of the sunflower lemma. Okay, so what are we trying to do with lifting? Let me just remind you, you have this outer function f and this inner function g, and together, you compose them to compute some big function, capital F, where Alice is given the x's and Bob's given the y's. And we want to show that if you have a communication complexity protocol for this lifted function, that you can extract from it a decision tree for little f. Okay? So in other words, even though this could look really complicated, they could be computing parities and who knows, all kinds of complicated, even uncomputable, very hard to compute things that you can sort of nonetheless decompose it. So really, they're just sending bits about f. Okay, and this is sort of a picture of what the protocol looks like at a high level. So you have at the top, you have all of Alice's inputs, or all the rows, and Bob's inputs, or all the columns. So the rows are labeled with all possible inputs that Alice could get, all x's, and columns are all the ones for Bob. And let's say in the beginning, Alice sends a bit. So she sends a bit, and that bit partitions her inputs into 2 halves. So maybe these are the bits that these are the inputs where she would say 0, and these are the inputs where she would say 1. So that partitions the big matrix into these 2 submatrices. Okay? And then Bob speaks, and he further partitions this matrix into 2 submatrices, and so on. Okay? And finally, at the bottom, they have, the bottom consists of all these little submatrices, and they have to be monochromatic. So there has to be one answer that's good for everything in that little subrectangle. Okay? And the main piece of the argument is more or less to track how much information, and this is blockwise, right? So remember what x is. It's a whole bunch of blocks, n different blocks. Each block is log m bits. Okay, let's just think about x. Forget y for now. Okay, so x is a vector. It's broken up into n blocks, and each block has log m bits. And we're going to just track like how much information as we proceed down this protocol is sort of learned about the distribution over these x vectors. And as soon as we find that there's some blocks that too much information is learned about them, at that point in time we want to do the same decomposition. We want to find that block, the maximal block, fix the value for it, which decomposes the set x into these nice spread pieces. So this is just definitions that are more or less exactly analogous to what we did before. Dense exactly is the same thing as being not sparse. So the distribution x is dense if for every subset of blocks I, the probability that the number of extensions, the projection to I, so how probable it is they're all it's spread. They're all basically equally likely, modulo a little parameter. And the main thing that we do is take all of x, for any rectangle, take all of x. If it's not spread, then we find the block I1 maximal block that we know too much about. Find a particular setting for it, just the same way we did in the sunflower theorem. Look at x restricted to all the sets that are consistent with that value alpha 1. Okay, that'll now be nice and spread out. So that'll be spread, and then we continue. So take x minus this part and continue. Okay, and this gives us a really nice decomposition. And these alphas here are going to play the same role that they played before. So they are going to be the blocks that we're going to fix and we're going to query in the decision tree. We have to deal with the Y part, but this is like the high-level idea. So I'm out of time, so I'll stop. There's many other applications of lifting, but I think I don't want to run over, so I guess I'll stop there.
Thank you.